Good morning, everyone. So as you know, the space restrictions in the labs have made for a little bit of a strange lab schedule this semester. I'm going to take a few minutes in this video to give a very concise introduction to assembly for those of you who are doing the assembly lab this Tuesday. And so some of this is ahead of a lecture by a little bit, but the gaps will get filled in soon enough. So assembly is a kind of programming language, but it's a special programming language in that it's designed so that every single assembly instruction corresponds directly to a hardware instruction. So what we'll be doing over the next few weeks is slowly putting together a CPU, and the hardware itself has individual instructions that the hardware supports. Now, when you write code in like C or Java, every statement in C or Java usually takes up 5 or 10 or more individual hardware instructions, and we group them together in a high-level language construct because it's easier for us to program. But assembly is at the other end where you actually get to see the individual steps the hardware is taking. Like I said, over the next few weeks, we'll take a closer look at exactly what those hardware instructions are. But for now, we're going to be doing some very simple assembly programming just to get you started and get those wheels turning. So here's what your model is for the first week. For the first week, you can think of assembly as a programming language where you're given 32 predefined variables, and that's all you can use. And these variables have two different sets of names. One of the sets is just numbers. Their names are $0 through $31. And you can use that, it works, but they also have conventional names, things like 0, AT, V0, V1, A0, A1, and so on. And it's these names that are generally easier to use, and that's what I'm going to use in this video. So a few names, a few variables that you should be aware of. The 0 variable is always 0. So you can't change it. Anytime you use this variable, you're reading in a 0. Anytime you have a return value, so something you would normally put in a return statement, that goes in V0. So if in Java you're thinking, let's say, return 6, then what you'll do is you'll set V0 equal to 6, and that will have the same effect. Parameters go in your A registers. And then your scratch space, the variables that you pick up and use as you do calculations, are your T registers, T0 through T8. These are where your temporary variables go, your temporary values go. So what you have now is you have a programming language where all the variables are laid out for you. You're mostly going to be using V0 for return values, A0, A1, A2 for parameters, like function parameters, and T0 through T8 for everything else. And so now, what do your commands look like? Your commands for what you need for the first lab are all just unary and binary operations. So if we're thinking in terms of Java, you're doing stuff like x equals y plus 6 or x equals y plus z or something like that. In assembly, we have to use our predefined registers, so it might look something like this. Oh, and then the other thing about assembly is the name of the command comes first. So in Java, we're saying like y plus 6, and we just put the plus in the middle. In assembly, the command comes first. So what we're going to do is add, and then just like in Java where the destination is on the left, we're going to put a new value in T0, and that value is going to be equal to the sum of two other registers, let's say T1 and T2. Now, if you want to add an immediate value, or that's the assembly way of saying a constant, we use add I. So maybe we're going to put into T0, T1 plus the literal value 6. So for this lab, you're going to be doing just some basic commands, basic ALU type commands like add or add I, subtract, and or not, things like that, right? So the logical operations, like in Java, you can say x equals y and z. right? You can do the same thing in assembly. You would just put the command first, and T0 gets the AND of T1 and T2. Now, these are what we call bitwise operations, if you haven't seen those before. And what that means is, if you give it two numbers and you do an AND of two numbers, it's doing an AND of the individual bits. So remember, we talked in class about what it means to do this. If I have two 5-bit buses coming into an AND gate, that's shorthand for doing an AND on each corresponding pair of bits on those two buses, and then bundling them all back together. That's exactly what this is doing here. So for example, if X is equal to the binary number 0110101 and Y is X and Y is just an AND on each corresponding bit. So 0, 0, 1, 0, 0, 0, 0. The only one in there is the column where there's two ones. So that's what we mean by a bitwise operation, and that's what your AND and your OR and your NOT and stuff are going to do. Now with NOT, you have to be careful, because let's say X is equal to 0, and then we do not X. Normally when we do a NOT, we're thinking about switching between true and false. So if we're thinking that 0 means false, and then we do not X, remember we're going to do that NOT on each individual bit, so we get all ones. And if we're trying to look at a single one as true, if we want 1 to be true, then that doesn't line up with what we're looking for. So we need to do one extra step to make this clean for purposes of the lab. And that is, we want to strip away all of those extra ones. So here's the trick. If we have, let's say, Y is equal to all ones, but we want to get rid of everything but the least significant bit, we use something called a bit mask. So we'll say that the mask, and what that mask will be is just a constant 1. Because now if I do Y and M, then that bitwise AND will pass through the 1, but the zeros here will zero everything else out. So you'll notice in the lab instructions it says after you do a NOT, do an AND, and that's Y. So let's say I have a value in T0 and I want to do a NOT of T0. I can say NOT T1 T0, right? That'll flip all of the bits in T1, but then I want to apply this mask here, so I can do AND I T2 T1 1. That's my mask. And what that will do is it'll make sure that all of the bits are 0 except for the very last one. All right, so with that by way of introduction, let's take a look at some real Mips assembly code. So we'll be using a program called Mars that you can download, and that will be the IDE for our assembly code. And so what you can see in Mars is you have an editor window and some nice syntax highlighting. Over here, you can see your list of registers. So you see they have both a number and a name. So the number here goes from 0 to 31. We can reference them by number, but that's usually not the easiest code to read, so we can reference them by name. For right now, the names you need to know are 0. That's just a constant 0. It's always equal to 0. V0 is where your return value goes. A0, A1, A2, and A3, you see it says argument there. Those are your parameters. And then T0 through T8, so they're up here and down here, is your scratch space. So let's say I want to write a function that just doubles a value. So I give it an input and it returns twice that value for an output. So first you have to declare a function, and in assembly that is just the name of the function followed by a colon, and then you put in your code. So you see here in the code, if we want to double a value, we just add it to itself. Now notice we don't have a signature here or anything. Parameters just come in on the A registers. So there are my inputs, A0, I can just use them. And so I just take A0, add it to itself. And since I want that to be my return value, I just make sure that the destination is V0. Whatever's left in V0 is the return value. So I added two inputs. I put the result in the return register. And then the piece of magic for today is JRRA. It stands for jump register, but you can just think of it as a return statement. So what that's going to do is cause the function to end or return, and it returns whatever value happens to be sitting around in V0. Here's a method called triple. It has a bug in it, but the idea here is that we added A0 and A0 together. We added A0 again, leave it in V0, and that should be 3 times the A0 parameter. Yeah, but there's a bug in it, and so that's part of your startup, is to figure that out. A couple other things here to notice. Here's another magic line, that global line. It just makes the double and triple names available outside of the code. It's like an export statement. The autograder needs that. And then the dot text just says here, this is where my code begins. So you're going to be writing some functions in assembly, and they're all going to be doable just with simple math like add, subtract, or if there's logic in it, you're going to be able to do that with the ands and the ors. You won't need any if statements or anything. You're welcome to look up how to use that if you want, but you will be able to do your ands and ors simply in line. Occasionally, you might have to grab that mask. And so when you want to run the code, there is the assemble button. So when you assemble the button, you can see it turned into machine code. That will be meaningful later. And then you can click this button here to step through your code one line at a time. And as you do that, you can see how the values of the registers change. So here's the lab. You get the starter code from the GitHub Classroom link. MUnit is like DL unit. It's the auto grading software. Mars is what we were just looking at right here. And we got the command line and stuff. The workflow is very similar to DL unit. And so what you'll do is you'll write some code in Java using the coding bat, and then you'll convert it to assembly. This time though, GitHub is not going to do auto grading for you. It's up to you to test your own code. These functions for the first day are pretty simple, so you should be able to test them thoroughly. Coding bat will give you some idea on some test cases. And remember the not and the and I down here. Okay, so that should be enough to get started. A little bit of trial and error, I'm sure, will happen as you get going with this, but I will do my best to keep my eye on the chat. By all means, help each other out if this is something that comes a little more easily to you than to others, and have fun with it. I wouldn't want to write a whole big program in assembly, but it is kind of a neat way of thinking about how the computer works, at least for a few assignments.